Yeah. Okay, so I would like to talk about quantum spin Hall effect of light and photonic analogs of topological insulators, namely bringing ideas from fermions to bosons. Of course, the difference between them are obvious. Anyone can see difference between fermions and bosons, but the analogies is the one I would be focusing, which are not so obvious. So this work was essentially driven, all of this project, by Konstantin Bliok, and then some papers, about a few of them, like 3 or so with Bekshaev, a couple of them or so with Daniel Lakem, is the next speaker, one paper with Smirnova, one with Max Klein. But the driving force of these works are essentially Bliok. So Konstantin. So I'm going to give a brief overview of some of all the results, and then let me just put the pointer here, laser pointer here. And then I'll be focusing mostly the last paper. And then for the first part, the second part, I would like to focus on how to bring these ideas from photons to surface acoustic waves. And this work done in collaboration with Dan Lakem, one paper, Dress one paper, but the driving force is Konstantin Bliok in all the other papers, including how to look at transverse spin and surface waves in acoustic metamaterials, how to look at spin and orbit angular momentum of acoustic beams, looking at the Klein Gordon representation of acoustic waves and topological origin of surface acoustic waves. This would be acoustic mode. That will be the main part of the second talk, because it's the topological aspects are mostly in that paper. It's a PRL a few years ago. We also look at acoustic radiation force and torques, and acoustic versus electromagnetic field theory. This is with a group of Justin Dressel, and then with Daniel Lakem, H modes in two-dimensional electromagnetic slab waveguides, looking at analogs of acoustic plasmons. So of course, these systems are all different from each other. This is obvious even to a high school kid, but what's not obvious, which are the analogies. So the focus of many of these slides today will be analogies between very different problems. And also this year, we're looking with Kostya Bliok and his father, essentially ponderomotive forces, Stokes-Drist momentum in acoustic and electromagnetic waves. Again, looking at many analogies. So there will be many, many analogies today. So let's start with a brief overview of the electrons and then go quickly on the light part. On the electron, on the quantum Hall effect, you have spin up and spin down H states moving in the same direction. The quantum spin Hall effect, they're moving in opposite direction, and the field is zero in the middle. So for all of these, electrons flow through the edge, and the rest is insulating. So that's for in electrons. So the key edge is to look at the spin momentum locking. Opposite spins propagate in opposite directions. And the 3D topological insulator is a 3D generalization where there are these 2D surface modes, which are helical massless fermions with spin momentum locking. We had them in real space, momentum space. So now let's look at the photonic counterparts of the electronic spin Hall effect, in particular the quantum spin Hall effect of light. So we need to look at surface modes with spin momentum locking. So that's our goal here. So people have been looking at photonic topological insulators in complex metamaterials. We're not looking at this. We have shown that pure free space light already possesses intrinsic quantum spin Hall effect, and that simple natural materials like metals, they all support surface plasmon polarity modes, exhibit some features that resemble topological insulators, even though they are very, very different. Some of them are fermions, some of them are bosons, some of them are massless, some of them have zero mass. The differences are obvious, even to a kid, but the analogies are not so obvious. So we're focused on the analogies here. The transverse spin in evanescent wave, we have been working on this for some time. We started 2012, 14, and spin control, unidirectional excitation of surface modes or waveguide modes can be interpreted as manifestations of the quantum spin Hall effect of light. So the bulk modes, these are the basic spin properties of light. The bulk modes for free light are propagating plane waves. with this sigma is the helicity. Could be either counterclockwise or clockwise, and the photons carry intrinsic angular momentum, namely they carry spin. And this is longitudinal along K, so it's along the direction. There's a spin here, and it's helicity-dependent spin. So this is for free light propagating plane waves. So there is a helicity, longitudinal, helicity-dependent spin. And this is what you see in textbooks. They propagate like this. So now, in the case of an interface between a metal and a vacuum, the K in the vacuum becomes imaginary. So therefore, the wave becomes evanescent, decays exponentially. When you put this imaginary, the electric field is not propagating in the XY plane, it's not rotating, but it's rotating in the XZ plane, forming a cycloid. So there is a cycloidal XZ plane rotation of the electric field generates the transverse spin as transverse here, because you're rotating like this, and then this gives rise to a momentum which is transverse. And the sign of transverse spin depends on the direction of propagation of the evanescent wave. So therefore, when you have an evanescent wave, you put the K imaginary, so therefore the E decays exponentially. This is an evanescent wave away from the metal. And then you can get, instead of longitudinal, you get a transverse helicity independent spin. Before was longitudinal helicity dependent. So we began working on this about 10 years ago, and then we get longer work with Bekshaev in 2014 about this transverse helicity dependent spin. You can see this by looking at the classical analog of ocean waves, where near the edge, even though the momentum is left to right on this green arrow, there is this angular momentum here pointing away from the plane. So this is the transverse spin, which is large at the edge, but then becomes smaller and smaller when you go to the bulk. So therefore, and this has to do with the fact that just put on the Maxwell equations this, and you get this right away. It's a cycloid. It's just a simple derivation. The nature of this transverse spin is similar to the circular motion of water waves in the ocean. And then, so let's look at this here, this animation here. Let me see if I can get the animation working here. The back here, perhaps. So I need to perhaps remove the pointer options here. And then, let me see here. Here it is. So click here, perhaps on the next one here. Okay, good. Click here. Okay, there it is. Let me just remove the, I'm sorry. So here it is. So you see the angular momentum here, which is very large. So the momentum linear is left to right, but there is this transverse momentum. Of course, it goes to zero once you go to the bottom here. So therefore, this is the extraordinary momentum and spin in evanescent waves that we studied with Bloch and Bekshaev some time ago. And then it started like a decade ago, and we had some extensions in different cases. If you look at Born and Wolf, Book of Optics, Jackson, E&M, Landau-Lifshitz, they all tell you the momentum of light is determined by the Poynting vector. They all tell you the momentum of light is directed along the wave vector and is independent polarization. And that the spin angular momentum of light is determined by the circular polarization is directed along the wave vector. What we found is that our results challenge the textbook statements when you are near the edges. But for nano-photonics, edges are everywhere. Surface dominates. So therefore, what you read in the textbooks, which essentially it just doesn't work. Initially, we had some friction with referees like 10 or 12 years ago on this, but then eventually there are many experiments now that have proved that all these points are correct. So therefore, this is an experiment done in collaboration with some friends in the UK. They were looking at direct measurements of the extraordinary optical momentum and transverse spin-dependent force using nanocantilevers. So there is the light incident here, bouncing here. There is the radiation pressure in the longitudinal direction. There is a weak spin force, perpendicular one. So they're measuring the blue one and the pink one, which is about which is much smaller, about like 10 to the minus about 100 times smaller. So the cantilever, they can measure the blue one, which is the standard one, and the pink one, which is the spin momentum here. And then they look at the blue, which is the standard one, is piconewtons, and the pink one, which is like about 100 times smaller, and we can do theorem experiment, good comparison. So the prediction has been verified using these cantilevers, but was also verified by three-dimensional measurements of the helicity-dependent forces on a me particle, on a small particle on a surface. This is the group of Federico Capasso at Harvard. They had a beautiful work published a few years ago, where they report the simultaneous measurement of all components of these optical forces in 3D force spectroscopy, femtosecond sensitivity. The vector force fields are compared quantitatively with our theoretical calculations, and then when they change the polarization state of the incident light, there was excellent agreement. So they have a visual evidence of the effect of spin momentum on the Poynting vector of an evanescent optical field. And this is important for nano-photonics because there's many surfaces. The evanescent fields are important. So this unusual transverse spin independent polarization survives in the T and TM surface modes. Opposite direction of propagation correspond to opposite transverse spins. So this is essentially the quantum spin Hall effect of light. And this was in this paper with Derek Smirnova and Kosti Blyoch. And then, so now there is an analogy here. So we replace the topological insulator, which is here on the, let me just do the pointer again. Oh, there it is here. If you have the vacuum, you have a perfect topological insulator, you have a perfect Dirac cone. In a material, there's always surface impurities and dislocations, stacking fold. There's always like all kind of garbage impurities. In the case of the vacuum, it's a perfect Dirac cone. It's absolutely perfect. We replace the insulator by a metal because the metal is an insulator for photons below the plasma frequency. So and then the surface plasma polaritons give you these edge states here. So the metal vacuum interface resembles, using a condensed matter analogy, the interface between a semi-metal and an insulator. So therefore, we essentially extended the analogies from electrons to photons, because we like analogies here. The optical filament has been observed in many experiments. Some involve surface plasma polaritons at the metal vacuum interface that resemble the interface between a semi-metal and an insulator. The surface plasma polariton modes exhibit spin momentum locking, which are typical for electrons in quantum spin Hall effect states. So several groups have independently reported experiments on these spin-dependent unidirectional excitation surface waveguide Maxwell modes. They all have a system like this, where you can have a transversely incident light with the usual spin, so you can change the helicity, either blue, inducing the blue response here, or red, inducing the red or orange response here. So there is a scatterer. You couple the surface modes, either via particle or directly incident to the surface, and there is a spin-dependent direction of the surface modes. So this is the underlying situation from many experiments. You can take a nanofiber, put a nanoparticle here, incident the light, but you can do the polarization either to the left or the right, and you can get photons either to the right or to the left. Or you can take here a photonic crystal waveguide, incident light with the helicity to the left or the right, and you can get photons to the left or the right. And the reference are below. Or you could do this with surface plasma polaritons. You can actually control the excitation of the surface by changing the helicity from a distance. You have complete control in the surface mode from far away. So this adds control on the surface modes here. So we have shown that the pure free space light already possesses intrinsic quantum spin Hall effect. The simple natural materials, such as metals, supporting surface plasma polariton modes, exhibit features that resemble topological insulators. Obviously, they're not the same. This is like just obvious from a mile, but what's not obvious are the analogies. So we show that the transverse spin in evanescent waves, I've been working for this for some time, initially was like a theoretical thing that people were doubting even existed. And then there were a whole bunch of experiments confirming the spin-controlled unidirectional excitation of surface or waveguide modes that can be interpreted as a manifestation of the quantum spin Hall effect of light, because there is spin momentum locking, all of that. So therefore, light itself possesses intrinsic quantum spin Hall effect, which means strong spin momentum locking in surface Maxwell modes. The transverse polarization independent spin in evanescent waves that originates from the transversality and the spin-orbit interaction of light is responsible for it. So the underlying mechanism is spin-orbit coupling of light, which is intrinsic, and the transversality condition. This gives rise to this transverse polarization independent or helicity independent spin in evanescent waves. It is different in origin from the quantum Hall effect electron, because these are vastly different, brutally different systems. This is obvious. Is spin momentum coupling rather than spinor momentum coupling. And the differences are obvious, but we're focusing here on the analogies. And, we're also looking at the following question. Can these very basic surface waves in Maxwell equation be described as topological surface modes? Do surface plasmons have a topological origin? So we have metal here, and the vacuum, and this longitudinal mode, momentum, and transverse one. So we're looking at this work here, topological non-Hermitian origin of surface Maxwell waves. And then the surface modes of the Maxwell equations are shown here. So you hear the permeability and the permittivity here, and the usual relations of the surface mode at the interface between two media epsilon 1, mu 1, epsilon 2, mu 2 has this TM polarization in blue, and the T polarization, transverse electric, in yellow. So these are the two polarizations here. So therefore, you can place the diagram where you can change epsilon 2 divided by epsilon 1 on one axis, and mu 2 divided by mu 1 in the other axis. When you do that, you take the ratio of epsilons and the ratio of mu, and you can get this reduced epsilon, reduced mu, and look at where in the diagram you get TM waves or T waves, namely when you get these waves like the blue ones or like the yellow ones. And then we did some work on this 2007, and then some more work afterwards. And then we're looking at the edge and how to try to understand this. The diagrams are deformed with the formation of the interface, but there are some general robust features. The TM mode can exist only at interfaces between the permittivity, where the permittivity changes sign. So the sign of the ratio epsilon 2 over epsilon 1 changes sign, and the T mode can exist only at interfaces where the permeability changes sign. Why is this so? Is there any fundamental reason for this? So therefore, let's look at the topological surface mode of the Dirac equation. In this case, we have here momentum M, you get diagonal off diagonal. The surface mode can appear at the interface between two media with different masses. This is from Jackie Rabbit. This is from 1976. It's a very old result. The same mode occurs in 2D and 3D. That's a zero mass spectrum at the edge. So here there is there's a spectrum here, and then the red, blue changes to blue, red, from block 1 and block 2, and then the gap goes to zero at the surface. The Dirac surface mode appears on interfaces where the mass changes its sign. So therefore, it's this is related to the non-trivial Mobius strip Z2 topology Dirac Hamiltonian and bulk eigenmode. So you have M1 positive, M2 positive. There is here, let's say, red, blue. But if you change from positive to negative, you get these edge states, and the red goes to blue and blue goes to red. So the Dirac surface mode appears only at the interface where the mass changes sign, and is related to this topological feature here. And then you can introduce topological Z2 invariant related to the change of the mass sign. And there is a bulk boundary corresponding with determine the number of surface mode n by taking this difference here. It can be the 0 or 1. You can present the flip of the mass when you go from positive to negative as a pi rotation in the complex plane. And you get this omega here. Now let's write the Weyl form of the Maxwell equations and topological properties of the helicity. There is a relativistic Dirac-Weyl-like form of the Maxwell equations, which is written like this. So you can write the Maxwell equations like this. It looks like the Dirac form, where P is this one here, and S are the spin 1 matrices. So you can write the EH of this form here with the curl gives you these relations here. And the key operator is the helicity, which is the projection of the spin along P. And it is 1/√, of epsilon mu, and it has epsilon mu in the matrix here. That has been worked by Majorana many years ago, Oppenheimer, Berry, many others. Then we recently were looking together with Alpejan and others on properties of these Maxwell equations in this relativistic Dirac-Weil form. This is very useful for the last part of the talk. So we need to keep this in mind, that you can write the Maxwell equations like this relativistic Dirac-Weil form. Helicity is very important. It's determined by the projection of the spin on the momentum direction. It is related to the dual symmetry between E and H. We have studied this for some years. Free space light has two helicity eigenstates, plus or minus, which is circularly polarized plane waves, either plus or minus here. The helicity operator in a lossless medium is generally non-Hermitian. The eigenvalues are complex. This makes physical sense. In a metal where this is negative, the momentum becomes imaginary. And when you get P imaginary, then you can get this decay. The spin polarization rotation remains real. So on the incident case, you get chirality 1, P and S in the same direction. The reflected chirality is -1. You can get P and momentum, essentially the intrinsic spin and the orbital spin, they are opposite directions. And the one within the metal decays within the metal. So the helicity changes sign in a negative index media. So you go from epsilon mu to minus epsilon minus mu because the momentum flips. So therefore, in this case, there is a change of the sign in epsilon and mu. And this is going to relate to topological properties. So we obtain properties of the photon helicity in 4 types of optical isotropic media: positive index medium, epsilon mu positive; negative index medium, epsilon mu positive; positive index metal, negative index metal. And this is the helicity operator here, where n is the index of refraction, this is epsilon mu. So this is a way to write the helicity operator here. More details are described here. The transition between these 4 types of media can be regarded as discrete rotations in the complex helicity plane. So you do pi/2, you map to epsilon negative mu positive. This is the origin here. And then you do pi, you're both negative, or minus pi, you get this one here. So this is the helicity version for light of what we saw before for fermions. So we can compare this with the Z2 feature Dirac Hamiltonian. Before we had this Z2, but in this case, there is a Z4 helicity winding number that has different values. There are 2 topological Z2 numbers, one corresponding to the TM mode, sign of epsilon change, and also the TE mode, sign of mu change. So therefore, instead of looking at the mass change, we're looking at the permeability change and the permittivity change. So this is fundamentally different. All previous work on topological insulators considered topological properties of Hamiltonian operator. We consider the topology of the helicity operator in the Maxwell equation. So we move from topology of H, Hamiltonian topology of the helicity. This extends the topological approach because you can have any conserved quantity operator can be considered. So in the 1D mode of Rebbe-Jakiv also occurs in 2D or 3D and has a 0 mass spectrum at the edge. So before we had here M1 and 2, there is this H state here. And if you change the sign, you get these states here with the Z2 topology. In that case, we had a topological invariant corresponding to the sign of M. And the bulk boundary correspondence was obtained like this. So instead of doing this rotation in energy plane between the masses, now we're going to focus on the helicity. So therefore, instead of focusing on what people are doing here, we're going to do on the Maxwell equation positive helicity negative, and then negative and positive. So the red-blue goes to blue-red, red-blue goes to blue-red. And instead of the gap going to 0, the helicity goes to 0, and you can get linearly polarized. So there is no circularly polarized anymore here. So there's an analogy between the electronic case and the Maxwell equation case. So in this case, the Dirac equation with a finite mass M, has this gap bulk spectrum. At the interface between the medium with opposite sign, the bulk spectra, this topological surface mode with massless spectrum. In this case, there is here opposite helicity states, and this bulk helicity eigenmode have opposite circular polarizations, and the interface controlled by the sign of the permittivity and the permeability support zero helicity surface waves with transverse electric or transverse magnetic linear polarization shown in green here. So there's many analogies between the fermionic case and the photonic case. So before we had the winding of the energy spectra in the Dirac-Maxwell equations here, and now we had the winding of the helicity spectra in the Maxwell equations below here. So this is helicity spectrum, and this is the energy. So again, winding of the energy, change the sign of the mass, and you get this energy spectrum equals a single zero mass surface mode. And this is the star here. But now, for this case here, we had the winding of the helicity spectra in the Maxwell equations. The change in the sign of the permittivity and permeability produces pi/2 pi rotation of the helicity spectrum in the complex helicity plane. This results in the appearance of one or two zero helicity transverse electric and transverse magnetic surface modes, which are these two stars here, the blue and the yellow one, described by the topological Z4 number. Is not Z2 anymore. And the medium index diagram showing the signs of the refractive index and impedance are these ones here, these four ones shown here. Now we went from fermions to light. Now let's push the analogy to surface acoustic waves. This is one paper in collaboration with Dressel, another collaboration with Daniel Lacan, the next speaker, but most of the work has been driven by Konstantin Blioch. He's the driving force of many of these papers here, in fact, all of them. And then let me focus mostly on the topological origin here, because that's what this conference is all about, but I need to do some brief introduction before. So here we have, instead of looking at the electric and magnetic field, we're going to look at the velocity and the pressure. So here we have two vector fields, here we have only one vector field. So there will be conditions on the topology is going to be mostly on, this will be two, change of epsilon and change of mu. In this case, will be only change of rho sign, because this one is vector field, this one is not. The constraints are these constraints, but in this case, the constraint for acoustic, this one here. The medium parameters to characterize the media's permittivity and permeability, but for acoustics are the density and the compressibility beta. Beta is the inverse of the bulk modulus. So we have here electric field replaced by the velocity, the magnetic field replaced by the pressure, the permittivity replaced by the density, and the permeability replaced by the compressibility modulus. So obviously these are different phenomena, but there are some nice analogies. They both have a spin intrinsic angular momentum density, which is given by E cross B and H cross H, in this case is V cross V. There is also a transverse spin density in an evanescent wave when you have a surface, which has a surprisingly, strikingly similar form. We're very pleased by this. There are surface waves, in this case is Tm and T. This is only one Tm-like, because there's only one vector field. We did also dispersive correction, but I'll not be talking about this, more technical. We did many, many things I'll not be talking today. We also did the relativistic version of it, where you can have the Dirac-Weil form, where you can put the electric field and magnetic field in a represented as a wave function-like representation. The dot product has this form here, epsilon and mu, and you can get the energy density for electromagnetism and for acoustics. As you can see, the forms are very similar, and the flux density, pressure times velocity, and E cross H. There's a connection with relativistic wave function. This is, of course, this is like a notation. You can look at the real part, imaginary part, and the relativistic wave equation. So there is like a similar forms for ENM and for relativistic. There's a 4 momentum operator, And the topological indices here. This is for the change of sign of the permittivity, and this for the permeability, and this for the topological indices for the density here. So there are many analogies between the electromagnetic case and the acoustic case, and we reach here from the fermionic case. So we're essentially extending the analogy, but notice here that the key quantity here is the density here, because we only have one vector field, which is V. Before we had two. So we had epsilon mu for each vector field, and now it's only one. So we have the waves could be longitudinal, like sound or P elastics. The same happened with earthquake. There is P waves and the transverse S waves here. And then you can see some of these. It's imagined to be like corks on the surface of the water, and you can monitor how the cork is going up and down. But you can also look at these from the point of view of momentum moving in this direction and the angular momentum rotating in this direction here, which gives rise to angular momentum perpendicular to the plane pointing towards you. That's the transverse momentum. And of course, it is large at the edge, and when you go towards the bulk, it becomes smaller and smaller, and eventually vanishes in the bulk. So this is an edge state phenomenon. And then you can look at bulk electromagnetic waves, you look at surface plasma. As soon as you put surfaces, things change. And so now we initially were looking at analogies between these surface states, edge and surface states, with electron topological isolators from the electron case to the optical case. And then we're asking the question, well, can these basic surface waves in Maxwell equation be described as topological surface modes? Do the surface plasmons and metal dielectric interface have a topological origin? And we find that this is the case because we're looking at the questions here. This describes the medium. We're looking at the surface modes. And then we look at the phase diagram of these surface T and Tm Maxwell modes in this plane here, epsilon 2, epsilon 1, mu 2, mu 2. And then we found that the key was the change of sign of epsilon and mu. And then we thought, hey, wait a moment. This is similar to the Iraq case. They're looking at the sign, the difference of the mass changing from positive to negative, and you get the surface states. So therefore, we start studying the surface electromagnetic waves of topological origin related to the non-Hermitian helicity operator. Now, the helicity is ill-defined and epsilon equals 0 and mu equals 0. That splits the plane, but that's okay because at these special values correspond to exceptional points of the operator, which are very interesting. So there is a modern theory, non-Hermitian of topological systems. Topological transitions happen at these exceptional points. And this is a separate object for a different talk, but this is a very exciting thing to study there. And then in our case, we have exceptional points of the helicity operator in a lossless system. So there are two eigenstates coalesce in the exceptional point and form a chiral state. So this is proportional to this, and then there is the epsilon mu or mu equals 0 limit. These are electric magnetic field state near the, it is called the epsilon near 0 and mu near 0 material. There is like a whole area of metamaterials, people looking at this small epsilon and small mu physics, which is very exciting. And this is a completely new non-Hermitian twist for this type of research. So therefore, we saw the surface electromagnetic modes within isotropic lossless media have a topological origin similar to the topological surface modes in the Dirac equation. The topology is the helicity rather than Hamiltonian, and the winding of the complex helicity spectrum is this one here. Sorry, you replace Z4 by Z2 and epsilon mu by the mass. The bulk boundary correspondence corresponds to this change of sign. Helicity is non-Hermitian. There are surface modes, can be dark, imaginary frequency wave vector. And the exceptional points correspond to these singularities here. And the chiral bulk modes occur in this index near 0 materials. So that's the summary for this part.
Excuse me, you have 10 more minutes. Okay, 10 minutes.
Okay, 10 more minutes, good. So now let's look at more careful at the acoustic sound waves. Good timing. So we look at this now, we're going to revisit this again more carefully now. So we had the surface waves here. So let's look at when you have the velocity, you take the divergence, you get the pressure. And if you get the pressure, you can get the gradient, you can get the velocity. So you can go back between the velocity field and the pressure field via a divergence and via, divergence or via gradient. Rho is the mass density and beta is the compressibility, which is the inverse of the bulk modulus. So therefore, let's consider transverse spin in evanescent acoustic wave. Let's start first with monochromatic acoustic waves. In general, they are non-monochromatic, and I'll show you the equations in a moment. But let's start with a simpler case first. Frequency omega in a dense medium. So you can get divergence gives the pressure, and the gradient gives you the velocity. The variables are the complex velocity and the pressure fields. The real value medium parameters are the mass density and the compressibility, beta, which is the inverse of the bulk modulus. So these are these equations support only longitudinal, that means curl-free waves, which follows from this expression here. These are not scalar waves. The velocity, v, determines vector properties of acoustic waves, even though these are longitudinal. For plane waves, there are these dispersion relation is on here. The longitudinality condition is on here. So there is the analogous longitudinal condition for Maxwell equation in this for acoustic waves is K cross V equals 0. The evanescent waves can be presented again as plane wave with a complex wave vector. So therefore, before we had the Maxwell equations right here, but we're going to replace the divergence equal to 0 by the curl of the velocity equal to 0. We're going to replace the curl of H by the divergence of P. The curl of H gives you E with epsilon, and the divergence of P gives you V with rho. So epsilon corresponds to rho and E to V. And here, the divergence goes to the curl, E goes to V, and P goes to H, and beta goes to mu. So this is the analogy. So there is electromagnetic acoustic analogy between EH, VP, and epsilon mu rho beta. Of course, these are different physics, different systems. Even a high school kid knows that. This is trivial. But the high school kid will not know the analogies. And we're focusing here on the analogies here. So the energy density and the flux, in this case, the electromagnetic one goes into the acoustic one. And this one, it goes into this one here. So we have this table, which I was showing before. Electromagnetic goes to velocity and pressure. There are some constraints, medium parameters, energy density, and so on. There is a spin, angular momentum density, transverse spin, surface wave conditions that have to do with the ratio of epsilon and mu and the ratio densities. The general expression for the time average spin can be written by noting the medium particles with mass density rho experience a displacement A via this. So this displacement here, which can be related to the velocity. So you can write this as an angular momentum, which is R cross P. But P is the momentum, and the momentum density is the velocity times the density. So this is the momentum here, velocity times mass density. And the displacement R is A. And you can write A in terms of V. And then you can get the omega down here. So you can get this expression from looking at the R cross P, essentially. That's the. So there are entirely similar contribution of oscillating electrons in optical media provides the material contribution to electromagnetic spin angular momentum. So in the electromagnetic case, there is here the electric field transverse to this. But when you go to a surface, there are these cycloid, and you can get the transverse momentum. In this case, in the bulk, you get this. When you get the surface, you get this transverse angular momentum. So this is the appearance of the transverse spin in transversal electromagnetic on the left, and longitudinal acoustic waves. These are the plane waves of this type have linear polarization, which are orthogonal and parallel to the wave vector. In B, these are evanescent waves. So this is in the bulk, and these evanescent waves. So at the surface, there are these effects here. The evanescent waves with orthogonal real imaginary parts of the wave vector inevitably have elliptical in-plane polarization because the transversality for Maxwell equation is K dot E equals 0 in this case. This is intrinsic to the Maxwell equation, but for the acoustic waves is K cross V condition. These elliptical polarizations generate the transverse spin S. So this is intrinsic from the Maxwell equations. You go from the bulk here to the edge state. So this is a summary of the origin of this transverse one, looking at the transversality condition, Maxwell equation, and the longitudinal one for the waves. And this is the origin of this spin angular momentum density here, which is transverse with one S here, while the real propagation, real case, this one here. So this is for the bulk, electromagnetic acoustic, and for the surface waves, electromagnetic and acoustic here, which we have it in a variety of different papers from the past few years. And this relates to this situation we described before. There is the longitudinal one, and there is a transverse one at the edge that becomes 0 when you go to the bulk. There are also acoustic surface waves analogous to surface plasmons. These appear at interfaces with negative density media, which is one here. So therefore, right now, we're not going to look at the sign of epsilon ratio or mu ratio. We're looking at the change of the sign of the density here, ρ2 over ρ1. And it is possible to do a relativistic formalism for acoustic and Maxwell equations where the key parameter is ρ, as opposed to epsilon mu. And the topological index will be, in this case, looking at the sign of ρ2 over ρ1 as opposed to the sign of epsilon 2 or epsilon 1 and mu2 over mu1. So in this case, there are two indices. In this case, there's only one. In quantum terms, the acoustic waves correspond to massless and spinless particles. Therefore, the fundamental quantum relativistic representation is the Klein Gordon theory because the spin is 0 for the acoustic waves. So you write the Lagrangian for the Klein Gordon equation, you get this 4 momentum representation. The energy is this one here, the momentum is this one here. This is standard in field theory. But then right now for the acoustic analogy, our wave function analog is this one here, pressure velocity, which can be written as this product here, where there is the product of the pressure, beta, weighted, and here by the velocity weighted by rho. There is a 4 momentum here. The Klein Gordon wave function is similar to the velocity potential, this one here. So by taking the gradient of this wave function, you can get the velocity, which is not too bad. This rho,
sorry, Franco, you have only 1 or 2 minutes for actual discussion, actually. So yeah, you have only
sorry. So therefore, so this is the non-Hermitian thing, and then you get the topological number, this one here, and then conclusions here. The surface acoustic modes, essentially we did the 4 momentum in the Klein Gordon representation, and then there is here Z2 is replaced by Z4 rho by this, and then this is the conclusions. And thank you very much.
Okay. Thank you very much for the very interesting talk. So we have a time for 1 or 2 questions. Any question? Yeah, please.
I cannot hear. Perhaps the microphone could be turned on.
Microphone is not working, I think.
Perhaps if you could repeat the question, could you repeat the question?
Is rho mass density?
Yeah, the rho is the mass density, of course, is the mass density here.
What does negative density mean?
I know in this case refers to the the ratio of density here is like it's a change. It's a change of value of the density. It has to do with the when the system decays is analog to having a negative k or a negative velocity, because you have a surface state. Essentially, there is like a decay. So there is an analog of a negative velocity and a positive velocity. So, and this relates to a positive rho and negative rho. But this is like happens when you have an interface, and you get this positive case, negative case, and any other question here?
So I mean, are you saying rho is not exactly mass density?
Well, in this case, C1 is a velocity c squared negative. It means there is like an imaginary number, because there is the surface mode indicates that there is like a imaginary k that corresponds to like a negative mass. It's has to do with the fact there is an interface between the bulk and the edge. So it's a surface mode interface, and that's why it gives you this positive and negative regime for the C1 square and for the K square and omega square. There are all these numbers that can be negative because there are these imaginary numbers involved. Otherwise, there is no way to get an omega square negative, because omega squares will be typically either real, omega will be positive. The only way to get omega square negative and C square negative is to have these imaginary components.
Okay, thank you.
Okay, I think we have to move on. Let's thank the speaker once again. Thank you very much.
Okay.